Hello everyone, welcome to the class. Today we will study about the matched filter and we will prove that it is an optimum filter for receiving the signals. Now we have already done the baseband modulation and passband modulation, but let's in one slide let's do the review of what we have covered till now. So we have a single pulse, which is a baseband pulse. The example that I have taken was of a rectangular waveform. Now, to represent the digital data in the form of ones and zeros, so we will use a pulse PT, which is plus 5 volt, for example, to represent 1, and minus PT, which will become minus 5 volts to represent 0. And if we take the Fourier transform of this rectangular pulse, what we will get a sinc function, and which is this is a low pass complex signal. This spectra gives us an indication that it is a low pass complex waveform. Now, if you want to send your digital data to a distant place, so we will do the modulation. So modulation is equivalent to multiplying the rectangular waveform PT with a sinusoidal waveform. So this will take this form. Now, if we take the Fourier transform of this waveform, we will get two sinc functions. One sinc function will be centered around f naught, the other will be centered around minus f naught, and this is a band pass signal, and it is a real signal because this waveform follows the Hermitian symmetry. Now we also covered what is the MERE-PAM. So because if we are representing within one simple period, if we are sending one bit of information, either 1 and 0, so it will be 2 PAM. But if we are combining two bits within one simple period, so there will be four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. So we can transmit through the channel that will become 4 PAM. So in general, we can say that it is MERE-PAM. What is M? M represents the number of levels. For example, 0, 0, 0, 1, 1, 0, and 1, 1, there are four levels, right? So, and how many bits are there? Two bits. In the example, if we take two bits to travel within one simple period, so that means four levels will be there and two bits will be there. So what is the relationship? 2 raised to the power b will be equal to m. So representing this number of levels, we will say that it is MERE-PAM, where b is the number of bits to be transmitted in one simple period. All right. So if let's say as an example, if PT is the pulse, so as an example, if we take four levels, we can represent the voltage levels as 3, 1, minus 1, and minus with a difference of 2 volts, right? We can represent the voltages. So 0, 0 we can assign minus 3 volts, 0, 1 we can assign minus 1 volt, 1, 0 we can assign 1 volt, and 1, 1 we can assign 3 volts. So these voltages, these waveforms will be transmitted through the channel. These will be the baseband pulses. That does not make any difference whether it is baseband or passband, because simply the waveform will change. Of course, it will be multiplied by the sinusoidal waveform. But as I explained in my previous lecture, that here in this case it will be PT, here in this case it will be P dash T, it will be PT multiplied by sine of 2 pi f naught T. F naught is the carrier frequency. So if we transmit this pulse, so of course, when it goes through the channel, it will become noisy. And then at the receiver end, we have to actually demodulate. That means we have to make an estimate of what amplitude we are receiving, because the noise will certainly uh, attenuate the amplitudes. So therefore, we have to making an estimate will be the job of the receiver, making the correct decisions. Demodulation can be done by integrating the received pulse. So whatever we receive here, we can integrate it. So let's say yt is the received pulse. We will integrate over one simple period, and that will give us the estimate of the amplitude, and from that amplitude we can make a decision whether 0, 0, 0, 1, 1, 0 or 1, 1 was transmitted. and this is our this is the decision rule in case of 2 p.m. As an example, I have taken here the decision rule, which is for the 2 p.m. That means one bit will be transmitted within one symbol period. If the estimated amplitude is greater than 0, we will call that 1 was transmitted. If the estimated amplitude is less than 0, we will say that 0 was transmitted. So all in all, this is the review of what we have done till now in the in the pulse amplitude modulation and how to demodulate the pulse amplitude modulated signal. And when it travels through the channel, it is affected by noise, and there is a noisy signal received at the receiver. How to demodulate? So that's what we have covered till now. Now let us look further. So we also have learned that if we pass this received signal through a filter with response P of capital T minus T. So this response, actually this impulse response is matched to the pulse in this fashion. P of T minus, I will explain this when we will proceed further. So if we pass this received signal through a filter of this impulse response, and we sample the signal after every capital T seconds, then we get an estimate of AK. So what is AK hat? AK hat will be AK plus NK. AK hat is the estimate of the actual amplitude that was transmitted. So of course the noise will be added into the transmitted amplitude, and we will be making an estimate at the receiver side. So demodulation using a filter HT equal to P of capital T minus T by passing through the filter and then sampling it at every capital T seconds. Now, this block diagram that I'm coming to is a very fundamental block diagram and a very important block diagram. So we must understand this block diagram thoroughly. So let us now investigate that if we use an arbitrary pulse PT. So what is the meaning of arbitrary pulse? Arbitrary pulse means it can be rectangular pulse, it can be a sinusoid, any shape of the pulse we are taking, right? So that we call as PT. We will, once we will finish 2-3 more lectures, we will be coming to know that the shape of the about the shape of the pulse, because that is the only aspect which is in the control of the designer. Everything is random in between. So designing a pulse will be a more practical choice to receive the signal in a significant with a significant amount of signal to noise ratio. And this pulse can be complex also, right? So PT is the pulse which is to be represented for 1 and 0. So XT becomes the transmitted signal. So because transmitted signal will be a waveform, will be a train of waves, because it is a digital bit stream 1010 and so on. So PT will be used to represent one bit, and combined all the waveforms of PT will give us the transmitted signal XT, which we have already done, and this will be our transmitted signal. AKs are the amplitudes T minus T minus K capital T. K going from minus infinity to infinity. This actually defines the transmitted signal XT. XT is transmitted. It passes through the channel. Let us say the channel impulse response is CT. Then with this impulse response, the transmitted signal will be affected, right? So we can model the channel as a channel impulse response also. So let's say CT is the channel impulse response. Now when this transmitted signal passes through the channel, it gets convolved with, that means XT gets convolved with CT, right? And I'm not showing noise here. In my next block diagrams, I will be showing the noise addition also here. But anyway, this is CT is the channel impulse response. So now this is received at the receiver. So RT, because after when XT is transmitted, it gets convolved with CT, right? We will get a noisy and a distorted signal. So we call that signal as RT. Now RT is passed through a receiver filter. We will see the characteristics of this filter. For example, in this example, we are taking this filter P capital T minus T. So we will see that what filter will be the optimum filter here, so that when the received signal is coming and is passed through this filter, what we will get at the output of the filter is yt. Let's denote it by yt, and then yt is sampled after every t seconds to get ykt, which is the estimate of the amplitude. Right. After the pulse pt gets convolved with ct, so this pt is the pulse, it gets convolved with ct, then let us denote it by p2t, and whatever I am calling pt, so pt is my original pulse, I am actually denoting from now onwards this pt as p1t. What is my p2t? P2t is the convolution of p1t or xt with ct. P1t is the pulse, xt is the train of pulses transmitted, right? So when xt gets convolved with ct, we call this pulse as p2t, right? Whatever the shape of the waveform that comes here will be called as p2t, and I am also saying that my original pulse pt, I am now calling it as p1t. I have explained it in this block diagram. So p1t is my original pulse, right? After passing through channel, this P1T gets convolved with CT, right, to give me P2T, right, and noise will be added here. Now I'm showing the addition of noise also here, which is NT or eta T. So P2T, this waveform will be received at the receiver. Let us say the receiver transfer function is AT. So P2T will now be convolved with AT, right? So P2T convolved with A to T will give me P3T. So you must understand the difference between P1T, P2T and P3T. What is P1T? P1T is my original pulse. It passes through the channel, gets convolved with the channel, we get P2T. Noise will be added, and P2T, when it is received at the receiver, will be convolved with AT. What is AT? AT is the impulse response of this receiver filter, and we get P3T. So that's what is explained here. What is P2T? P1T convolution with CT. What is P3T? P2T convolution with AT, right? So what is, if we replace P2T with this here, so what is P3T? P3T is P1T convolution with CT, which is channel impulse response, convolution with AT, which is receiver filter impulse response. So that's the distinction we must understand to proceed further. What are these waveforms? P1T, P2T and P3T. And what becomes my XT? XT is, you must make a difference between P1T and XT. P1T is a waveform that we have chosen to represent either 1 or 0. Right? XT is the transmitted signal, which is a combination of many pulses. Right? So that's why the sigma will come here. Sigma k will vary from minus infinity to infinity. AK is the mapping amplitude, whatever the bits was there in the symbol period, right? If it is 0001 1011 in the case of 4 pm, so that amplitude will be multiplied with the waveform, and actual transmit xt becomes the actual transmitted signal. So what is RT? RT will be the received signal, right? Before the receiver filter. So what is RT? RT will be XT convolved with CT, because XT is the transmitted signal. It will get convolved with CT, and plus noise will be added, right? Now this convolution of P1 T minus K capital T with CT is actually P2T that we have already defined, right? This is P2T. So my expression is changed to AK P2T minus KT plus NT. All right, this is my received signal, where it is pointing to RT is this point, at this point, before the receiver filter. Now after the receiver filter, RT signal will get convolved with AT, which is a train of waveforms, right? So if I put RT here, RT will be equal to RT, we have to put this value of RT here, Now I also know that when P2T gets convolved with A2AT, it gives me P3T. So that is why I get P3T minus KT here. Plus, of course, the noise, this noise, this no, let me just come to, yeah, this RT is also having noise. So this RT is passing through the receiver filter with the response 80. So that means noise will also get convolved with 80. So that's what is shown here. Noise also gets convolved with 80, right? And the YT becomes AKP3T minus KT plus NT convolution with AT. What is P3T minus KT? It is P2T minus KT convolution with AT, right? Because RT will get convolved with AT to get us YT. Now this YT has to be, because YT is what? YT will be the signal waveform received after the receiver filter. Then it has to be sampled every capital T seconds. Right? We will see that. So YT, but important thing to note down here is that YT is again a PAM signal. YT is what? YT is P3T minus. What is P3? P3 is a pulse amplitude modulated wave only. No doubt, the original waveform, which is P1T, is passing through the channel. It is passing through the receiver filter. Then it gives us P3T, but ultimately it is a PAM signal. Of course, it is a noisy signal, but it is a pulse amplitude modulated signal. So YT is again a PAM signal with a different pulse P3T, right? How should we design the receive filter? Now the question is that how should we design this receiver filter? This is very important. How should we design this receive filter? What should be the impulse response of this filter so that we get the maximum signal to noise ratio, because signal to noise ratio will be a metric which will define the optimum character of the filter, right? So we will have to investigate that actually. Now it leads to a matched filter. We have already seen with our examples that if we design a filter with impulse response AT which is matched to the pulse, that is AT, if we design AT equal to P2 star P2 conjugate T minus T. If we design a filter, receiver filter with this impulse response, what is this impulse response? The impulse response is P2 star T minus T. That means this impulse response is actually a matching of with this pulse P2T, because P2T, this waveform, and of course the transmitted signal will pass through the receiver filter. But if we design the receiver filter with P2 star capital T minus T, that means this receiver filter is matched to this P2T pulse. So therefore it will be called as a matched filter, right? So what is the characteristic of this P2 star T minus T? For example, if this is the P2T, right? So it is a shifted version, a flipped version of the what is AT or P2 star T minus T. It will be a flipped version of P2T. So in this case, it is same in this case as pulse is symmetric, because the pulse is symmetric, so we are seeing the same. But let's take this example. If this is a type of P2T, and what will be P2 star T minus T? It will be a flipped version of this P2T. So that is the impulse response of the filter. This impulse response of the filter is matched to the pulse in this fashion, P2 star T minus T, that is the flipped version of the pulse. And if we design the filter like this, if we design this receiver filter with this relationship between the impulse response and P2T, then we will see that we will get the optimum filter, and which actually maximizes the signal to noise ratio. So this is a matched filter. A to AT is matched to P to T. As explained, this filter is called a matched filter. To analyze further, let us assume we are transmit to further prove the concept of the matched filter. This matched filter AT equal to P2 star T minus capital T minus T to be an optimum filter. So let us investigate this and analyze this further. And we assume that we are transmitting only one symbol. and then demodulated. So what is the meaning of this? So my xt will not have now sigma because I am transmitting only one symbol. Sigma actually represents the train of bits, but train of pulses representing the bit stream. But here I am saying that I'm transmitting only one symbol. So that means xt will be ak p1. P1 is the original pulse, t minus kt. My output received will be ak p3 t minus. I'm picking the formulas from the previous slides only. P3 t minus kt plus nt convolution with at. So RT will be equal to ak p2 t minus kt plus nt, as I have already explained it. Now let us put this yt in the convolution formula in terms of the continuous domain. So what is yt? Yt is actually the what is yt? Yt is actually the what is happening here. So what yt is at this point after the receiver filter. So how I am getting my yt? Yt is actually obtained after the received signal. Let me come to this point. Okay, at this point. So what? How I receive my yt? Yt I am receiving after rt, which is the received signal, gets passed through the receiver filter, which is match filter. So that means rt is being convolved with at to give me yt. So if I put this convolution of RT and AT in terms of the continuous domain, then I will get this relationship yt equal to integral going from minus infinity to infinity, AT minus tau R tau d tau. And I also know that yt is to be sampled after every symbol period capital T. So I can replace this yt with a with the particular instant of the sampling with particular sampling instant as yk plus 1t. K is a index, right? So yk plus 1 capital T, actually this is the instant, this is the sample, this becomes the sampling instant, right? So that means this t, which is a variable, is to be replaced with this value k plus 1 t, giving me the sampling instance. And I replace this t with k plus 1 t, so I get this formula. Everything will be because a t in place of t I will get k plus 1 capital T and so on. So I can replace this. I will put what is R tau. R tau, I will use this formula of RT, which is AKP2 T minus KT. So that's what I am putting here. Correct? Okay. So this is my YK plus T. YK plus 1 capital T. Now what is my AT actually? This A of what is my AT? I am assuming that it has to be AT should be equal to P2 star. Let me show P2 star capital T minus T. So that means I am putting here, I get here, you must understand also the difference between AT and AK. AKs are the amplitudes, AT is the impulse response of the receiver filter. So when I am finding out the sampled version of this yt at every capital T second sampling instance, so I am doing it like this yk plus 1 capital T. So that means I am substituting the small t with the k plus 1 capital T. I will get this formula, and I have replaced this R tau with this expression here. And I know that what is this AT? What is AT? AT is equal to P2 star capital T minus T. So I will replace this A, the argument will be different, AT with P2 star capital T minus T like this. So I will get P2 star, and I have also got here P2 and this expression. So if I rearrange, so I can take out the AK, P2 star tau minus kt. This is for the P2 star is for the impulse response, which is 80, and I am getting this P2 values because from this point, right? RT values, replacement of RT with this expression. So I am getting this expression here. This is the noise component, this is the signal component, right? Now P2 star tau minus kt, tau minus P2 tau minus kt will be equal to P2 tau minus kt mod square. AK will be a constant, will be out. It is not dependent on time, and plus some noise factor. This will be my noise factor. I can denote this by nk. Now, if we do change of variable, if we do a little bit of change of variable and replace tau with t plus kt, right? With if we change this tau with t plus kt, then what will happen? We can do the change of variable inside the integrals. What we will get is that we will get p2t mod square integral going from minus infinity to infinity, which is actually representing the energy of the pulse plus noise. So I can replace this integral with the energy. So E will be E multiplied by AK plus noise. Energy of the pulse we can always calculate pre-hand because we know the pulse, we can find out the energy of the pulse. So energy of the pulse, and if we divide this factor with energy of the pulse, which we can find out, we can get an estimate of AK with noise, of course, right? If we know AK, when we will come to know after dividing this yk plus 1 capital T with E capital E, I will get AK. So once I know AK, the estimate of AK, then we can detect what symbol was transmitted, and E is fixed and we can pre-compute, we can compute beforehand. So yk plus 1 T, so we will get an estimate of AK plus of course noise will also be divided by the same factor of energy. So but still it remains noise. So after estimating AK hat, we can do demapping and get the bits which are transmitted. Now let's take one symbol period to be transmitted as shown below. So that means I am saying that I am taking only one symbol to be transmitted. So and I am representing that symbol with A naught P2T. So what is A naught? I'm extending my block diagram from RT. So that means RT is my received signal. It has to be passed through this filter AT. I get YT here. Then it is to be sampled after every capital T instance. So I will get Y capital T and the estimate of AK. What I'm saying is that I'm transmitting symbol A naught, which is my present symbol, which is transmitted. So it will be A naught P to T plus noise because I'm not showing that part of the channel. So once it passes through the channel, it will be affected with noise and the pulse becomes P to T. So A naught P to T is my present sample, present symbol that I'm interested in. And at this point, I will get A naught P to T plus NT. So let's investigate what should be the impulse response of the receiver filter, which is AT, which maximizes signal to noise ratio and its output. So what is my RT? RT is A naught P to T plus noise. This is my present symbol that I'm interested in. What will be Y capital T? Y capital T will be A naught. P2, because this pulse will get, this RT will get convolved with AT, right? So I can put it like this: A naught P tau. This is AT minus tau d tau. This is the convolution formula in the continuous domain, and of course noise will also be convolved with the same impulse response, which is AT minus tau d tau. So the first part is my signal part, the second part is my noise part. So I can break this Y capital T, which is the value of the output at this sampling instant capital T, which is equal to the signal part and the noise part. So YT is this. So this part is the desired part and this is the undesired part, which is noise signal. We want to increase the desired component. We can calculate energy of P to T as P to T does not depend on A naught and AT also, and we that means we can calculate the energy of the waveform because it does not depend on the filter response and the channel and does not depend on A naught actually what symbol was transmitted. Then we can divide by the computed value, but noise will be present. So I have already explained this. I can define a metric here, which is known as the signal to noise ratio. which is the yx capital T mod square, which is the signal power divided by the expected value of the noise, because noise is random, so we are taking the expected value here. So it is the numerator is the signal power, the denominator is the noise power, so that becomes the signal to noise ratio. We will try to calculate it, and then we will prove that the filter, which is AT equal to P2 star capital T minus small t. This filter actually maximizes the signal to noise ratio, and we will say that matched filter is an optimum filter. So we try to calculate the noise component, the expected value of the noise power. So if I represent it like this, so what is y and t? This is n tau at minus tau. This is the noise value, noise component. So if I have to calculate the power of this, so how can I calculate? This is of course the once we have to deal with the power because it's square here, so it will be n star t a star t minus t and multiplied with minus infinity to infinity. Of course this previous integral is also from minus infinity to infinity, n tau a t minus tau, because this is a square here, so we are multiplying the two factors like this. If this is the complex number, so we can multiply it like this, so we get this, the conjugate, right? And we also need to take the expected value. We can take the expectation inside. We will say n star t, and we will only we are using two variables t and tau just to calculate the the square value, right? So we say that n star t and tau we take common from both the integrals, and a star t minus tau, t minus t, and a t minus tau, d tau dt d tau, right? So we know that the noise is assumed to be y. That means one noise sample is not dependent on the other noise sample. So what is the difference between t and tau? T and tau difference is that t is one particular instant, tau is a different instant, right? The both are representing time variables, but just we are trying to find out the correlation. We are trying to find out the signal expected value of the noise power by establishing the correlation between the noise components. So n star t and tau. So we say that the noise, we are assuming it to be wide. That means there will be no relationship between one sample and the other sample. Both will be independent of each other. There is no correlation between noise samples. So this n star t and tau will be equal to delta t minus tau. That means this value, this n star t and tau is actually 0, except at all the points it is 0 except at t equal to tau. So we can replace this with delta, and delta t minus tau is a star the rest of the factor, and when this rest of the factor will be multiplied with delta t minus tau, we get a star t minus t and a t minus t, and we will then because tau will in that case go away, and we will get only one variable t, right? So energy is given by the energy of A is given by n naught by 2. This is which is the noise power. This is how we can calculate the noise power. This is a well established relationship. I need not to go into this. So A star t minus t, a t minus tau. So if we multiply these two, we will get this a t minus t whole square mod whole square dt, and not by 2, which is basically the energy of A. Energy of A means the symbol that we are trying to transmit. We have transmitted. So we get the energy of the symbol which was transmitted, because we assumed here that what we will do is we will transmit this symbol only now and try to estimate this symbol. So at the receiver end, after passing it through the filter, what we have got? We have got this energy of A, this factor we have got. Now signal to noise ratio will be given by, so this is my noise component. I have calculated it. I have calculated the expected value of the noise. And if you now look at the signal value, it is A naught integral going from minus infinity to infinity p to tau a t minus tau d tau. So this is my signal component. I will have to look for the now how can I solve this signal power, because I need to square the same factor which I was trying to describe just now. So I will square it. I have already calculated the average noise power. Now I will use the Cauchy Schwarz inequality, which says that if G1 and G2 are two signals, both complex, then G1 star T into G2 T dt mod square is will always be less than equal to individual signal squares G1 T mod square, and in the individual integrals, integral minus infinity to infinity G1 T mod square dt, integral minus infinity to infinity G2 mod square dt. And to solve our case here, we will assume that, let's say, G1 T equal to A star T minus T, right, and G2 T equal to P2 T. So I'm trying to solve this with the Cauchy Schwarz inequality, and I'm now saying that G1T, I'm assuming it to be like this, G2T equal to be like this, right? So SNR will be given by it's not the SNR, it is the signal power actually. At this point, we will get the, when we will divide this with the noise power, then we will get the signal to noise ratio. So we are trying to calculate the signal power here. So and we have said that G1T is A star T minus T, G2T is P2T. So if I replace these in this expression, if we try to put A star T minus T in place of G1T and G2T equal to P2T here, then use the Cauchy's Schwarz inequality. We will say that P2 tau, because what is my GT? GT is P2T, so I can put PT here in place of T, it will be tau, P2 tau. So what is my G1 star? G1T equal to A star. So since star is already there, so this star will go from A. So we will get A T minus tau d tau whole square. After using the Cauchy's integral, we will say that P2 integral going from minus infinity to infinity mod square of p tau d tau and minus infinity to infinity, and the second factor we can take as a it is a t minus tau whole square d tau. So I can, this is my signal power, so I can place my signal power here, and you will see that this noise power will be cancelled. That means mod of a t minus tau, this factor will cancel out with this factor, because I will be using the Cauchy's integral to separate out this single integral into two integrals. So one integral will go with the noise power, and what we will be left with is 2 by n naught, because it will be n naught by 2 in the denominator, so it will become 2 by n naught p2 tau whole square d tau. P2 tau is actually the um, energy of the signal. I'm using the Cauchy's, it is inequality here, but I'm using the equality to replace this single integral with two integrals like this. I will in the next slide explain when this equality will hold. Now Cauchy-Schwarz inequality says that equality will only hold when G1T is a constant multiple of G2T. So that means I'm assuming this is my G1T, this is my G2T. If G1T is a multiple of G2T, then only I will say that this equality will hold, and I can replace this signal power with these two integrals, and one factor will cancel out with the noise power and to get this value. Okay, so signal to noise ratio now becomes 2 by n naught E into E, because this is the energy of the pulse. Now it leads to equality only when G1T is this, G22 is this, when G1T is a multiple of G2T, and I assume that that multiple factor is 1. So I will say that what is my G1T? A star T minus T, and what is my G2T? It is P2T. So which proves the fact, and I can say now AT is equal to P2 star T minus T, which is matched filter. So that means I have proven that the signal to noise ratio will be maximum only if I use the impulse response of the filter to be P2 star capital T minus T. Mesh filter maximizes signal to noise ratio and it is an optimum filter. So SNR will be given by 2 by N naught E. So AT equal to P2 star. If I use the receiver filter to be P2 star T minus T, which is a matched filter. Okay. So that explains the optimum character of the mesh filter because it maximizes the signal to noise ratio. Thank you for the presentation. Thank you.